This is the second lecture in network security. So today we're going to talk about little bit math, which help us understand the cryptography. Okay. So today it's like a math about the cryptography. If you have any questions anytime, please stop by. It's basic things, but it's good to refresh your memory. As I told you in this class, that every chapter, okay, is a prerequisite for the following chapters. So we go from chapter 1 to 18, but it's very important that you know what was covered in the previous chapters. Otherwise, you're going to get lost. So it's kind of built up until the end of the lectures. The book is very well written. The PowerPoints are very well written also, and that will help you to, to understand the concepts. Also, the questions at the end of each chapter are very useful. Try to do as much as you can. That will help you to understand the concepts and actually go deep into the concepts when you do the questions at the end of the book. So we're going to talk today about modular arithmetic, congruence, and matrices. Simple stuff. It will be an easy lecture, but it's very important to refresh your memory, right? All right, so let's start talking about integer arithmetic. Okay, we're going to talk about a set of integers, binary operations, integer division, the divisibility. Okay, and we're going to talk about linear, Diophantine equations, and so on and so forth. So as you know, set of integers z has like positive and negative numbers, including 0. No surprise to you, right? Good. All right. So what are the binary operations? Binary operation means there's two sides and an operation to do in the two sides. So all of you, I'm sure you know, addition, subtraction, and multiplication. So usually you do a binary operation in two integers in here. The result will be part of the z group, the z set. All right. So if you do 2 plus 1, it will be 3. 3 is part of the set. It does not go to a different set. So this is examples of the operations that you have learned from your elementary school. Add, subtract, and multiply. And all you have to be aware of the negative and the positive, whether the number is positive or negative. All right. So the more serious stuff comes when integer division. So usually integer division, not necessarily to give you one result. I'm gonna give you the result plus remainder. Sometimes you're gonna have a remainder, right? Remainder for the data. So an integer arithmetic, if we divide a by n, for example, we get quotient and a remainder. The relationship is written like this. So a equals to the cube multiplied by n plus the remainder. All right. Simple division, and here I don't need to give you examples. And here, for example, a is 255 and n 11. So 255 divided by 11. You know how to do the process, all right? So you're gonna get equated cube, and you're gonna get r the remainder. So the result is 23, and the remainder is 2. So in the operation of the division, all right, so usually you get a positive number, which is the, n is positive, and you get the remainder, and the quotient could be negative or positive. The remainder, always we like to have it as non-negative number, either 0 or positive number. Okay. If it's negative, we have to convert it to a positive. So for example, when you use a computer or a calculator, R and Q are negative when A is negative. How can we apply the restrictions that R need to be positive? So for example, in here, okay, the remainder in here. So for example, when you divide, for example, 255 by 11, you're going to get it negative 23, and the remainder is minus 2. right? So the way to convert it to positive, you add a whole 11 to whole 1, which is 11, to the 24, it becomes minus 24, and you minus this from the 11, it becomes 9, right? You understand? So if you divide 255 by 20 by 11 by 11, you're gonna get 23 negative 23 as cube and minus 2 as remainder. Or what you could do, because this is the dividend, okay? It equals to a full of the 23. So you add 1 to it, so it becomes 24, and then you remove it from the remainder, it becomes 9. Simple operation that you have learned in school. Is it clear? All right?
Excuse me, Professor.
Yes.
I just have a question. Like, we have to add 1 with the dividend.
Yes.
Always we have to add 1 with
Add 1. How much is the 1 here?
minus 1 only.
1 equals to 11.
Mm-hmm.
So it's like when you add 1 in here,
Mm-hmm.
you have to add 1 to here, and you have to take 1 from here. How much is the 1?
Well, we will take 1 from here.
Okay. Okay. What we are trying to calculate in here? How many 11s? Right. So when you have okay, so when you say 255 minus 255 divided by 11 equals how much? Minus 23. And how much is the remainder? Minus 2. So how many minus 255? How many 11s in minus 255 is minus 23? Right? And the remainder is 2. So if I add 11 plus 11 in here, okay, all right, I have to minus 11 in here. Okay, so 11 equals to how much? All 11 minus 24. So in here it becomes 9. Yes.
You did minus 23 minus 11.
Minus 23 minus a whole, minus a whole. How much is the whole?
Okay.
Equals 11.
Okay.
Right? And the remainder, I add 1 whole. How much is 1 whole? 11.
Yeah.
11 minus 2 becomes 9.
Yeah, okay.
Okay? Simple math, yeah. Alright, so the graph of division, okay, so that's the case of positive A, and the case of negative A. Okay, so you have to if it's negative, you have to bring it to the positive. So by adding 1 whole, okay, to the quotient, okay, and then the remainder you add, you remove 1 whole, okay. So let's talk about divisibility, okay. So you know, sometimes if the remainder is 0, then number is dividing a number. So for example, when you say, okay, 4, so when you say 2 divides 4, that means if you say 4 divided by 2 gives you 2, and how much is the remainder? Equals 0. Alright? So some numbers divide numbers, and some numbers does not divide numbers. Does not divide means it give you remainder. It will give you a remainder. So if the remainder is 0, then we can say A divides M. If it's not, we say A does not divide M. Alright? Simple math. Right? So the integer 4 divides 32. Right? Because 32 divided by 4, how much? 8, right? It will give you 8. However, Okay, A does not divide 32. The number A does not divide the number 42 because we have a remainder of 2. Alright? So we have to be aware about that number can divide numbers and numbers cannot divide numbers. General rules or properties we call them. Okay, if A divides 1, then how much is the value of A? Plus or minus 1. That's the only option, right? Plus or minus 1. Okay, if A divides B and B divides A, then A is plus or negative B. So they are equal, but the sign could be equal or different, right? If A divides B and B divides C, then A for sure divides C. Alright? Alright, and the property number 4, if A divides B and A divides C, so A divides 2 different numbers. Okay? A divides 2 different numbers. So the rule says A also will divide, okay, the B and the C when they are multiplied with any arbitrary numbers. So A divides B and A divides C. So the rule says A will divide B plus C if they are multiplied by any arbitrary numbers. Okay? Any arbitrary numbers, when M and M are arbitrary numbers. Alright? So to make it simple, make M and N 1. So that means A will divide B plus C. Right? Or any number. We're going to use it later. Okay, remember that we're going to build an algorithmic boxes. We're going to do a lot of operations. So now it looks simple, but when you start using it, it might get a little bit complex. So we have to start small and grow. Alright? So, as an example in here, 13 divides 78. 7 divides 78. Minus 6 divides 24. Okay, and so on and so forth. However, these numbers, for example, 13 does not divide 27. And so on and so forth. Right? For property 8, we say 3 divides 15 and 15 divides 45. So that means 3, it divides 45. We said A divides B, B divides 45, then A divides C. Okay, so 3 will divide 45. Same thing in here, 3 divides 15 and 3 divides 9. So if you use, so 3 will divide 15 plus 9 when they are multiplied with any arbitrary numbers. So the arbitrary numbers in here is 2, we choose 2 and 4. So if you do it, 3 divides 66. Okay? Just a property that you have to know. Okay. So, fact 1, the integer 1 has only one divisor. You agree? Itself. Alright. Any positive integer has at least 2 divisors, one and itself, but it can have more. So any integer can divide itself and can be divided by 1. What we call it, if it only can divide it by itself and 1. Prime number. Okay, if there is other number, then it's not prime, right? But at least every integer will divide itself and it could be divided by 1. You agree? Alright. So let's come to a new term, which is common divisor of 2 integers. So, if you look at the divisors of 144, these are all the divisors. The divisors are for 12, and you know how to calculate that from your math classes, right? For math classes, so what we have in here, for example, 12, okay, divided by 2 gives you 6. Divided by 2 gives you 3. Divided by 3 gives you 1. So what are divisors? 3, 2, 6, and 1. 4 divisors, which are, and itself, of course, divides itself by itself. So you have the 12, you have the 6, the 3, you have the 4. Okay, what's the 4? Where is the 4 coming from? 2 times 2, 4, right? Okay, and where is the 6 coming from? 2 times 3, or it's already here. Okay, so these are the divisors, right? You could do it also for the 140. But if you have two numbers, there is a group of digits, they call them common divisors. Common divisors. So 2, for example, divides the 140, and it divides also the 12, and so on and so forth. So what we call this area common divisors of 140 and 12. Common divisors. Okay, sometimes you need to calculate the common divisors. So the list now, there's a term now coming to the greatest common divisor. So the greatest common divisor of two positive integers is the largest integer that can divide both integers. So what is the greatest common divisor in here? 4. Okay, it's 4. All right. So for that, I mean, for two small integers like that, it's easy to calculate it. Do you agree? You do like this. But if I ask you, I need the greatest common, and by the way, one thing in encryption you need to know that we use a huge numbers. So if I tell you, okay, I'll give you like 5 minutes if you can calculate this for me. Okay, I need to calculate the great common divisor. Go ahead. Can you? All right. And that's a small number in cryptography. Usually it has like 28 digits or whatever, right? So definitely, we are not here teaching you how to calculate the common divisor and the great common divisors for small numbers, right? So the greatest common divisor for A and 0 is A. And the greatest common divisor for A and B, the greatest common divisor for B and R, where R is the remainder of dividing A by B. So if you divide A by B, there is a remainder, R. All right? Then the greatest common divisor will equal to B and R, where R is. So here we're introducing you to Euclidean. Okay. So that's what we do in Euclidean algorithm to calculate the greatest common divisor. Okay, we put R1 equals A and R2. Remember that there is two numbers. We're trying to get the greatest common divisor, right? So R1 equals to A and R2 equals to the other number, which is R. Okay, we divide them, we put the remainder in here, and then we move the remainder to here, and the second letter to here, and we do the whole process. We keep repeating until we get 0, then the greatest common divisor will be R1. Okay, alright. So when the greatest common divisor, A and B equals 1, we say that A and B are relatively prime. There's another term. There's a prime number, and two numbers are relatively prime. They are relatively prime only in one condition: if the greatest common divisor equals to 1. 1, right? That means there is no common divisors except 1, because 1 divides any number, right? No one divides any number. So when a greatest common divisor A and B equals 1, we say that A and B are relatively prime, relative primes, and most of the encryption algorithms, okay, depend on the prime numbers and relative primes, as we'll see later. So these are very important terms. So let's take a real example, okay? So again, okay, can you calculate for me in your paper right now what is the greatest common divisor between 2,740 and 1,760. So you have 1 minute. Try it. 5, 11, and 2. The greatest. I'm looking for the greatest. So let me teach you an easy way. Okay, we use Euclidean. So what we did in Euclidean, we put the first one as R1, which is in here. We moved it to here, and this number 1760, we moved it in here. That's R1 and R2. So the quotient and the remainder. So if you divide this by this is the quotient. How much is the quotient? 1. The remainder is how much? 980. So now you move the 1760 here, and you move the 980 here. You do the process again. The remainder is 780. You move the 780 here, and the 980 here. You do the process. How much is the remainder? 200. You move the 200 here, the 780 here. How much is the remainder? 180. You move the 180 here, 200 here. Remainder is 20. You move the 20 here, the 180 here. Okay, how much is the remainder? 0. You move, we keep remember in here, we keep the process until the remainder is 0. So we come 0. So now R1 is what? Is what? The greatest common divisor. Greatest common divisor. Alright? So, yes.
Sorry, R1 and R2, they are supposed to be subtracted to get R, right?
What?
You subtract R2 from R1 to get R.
I don't subtract. I do the division. I divide 740 by 1760. The quotient will be 1. The remainder will be 980. Okay? So the Q is the quotient. The remainder is in here. Okay? And they keep repeating the job. Alright? So Euclidean tells you the remainder when the 0, then the R, when R2 becomes 0, then the R1 is equals to the greatest common divisor. Alright, so how easy to program this, to write a code? Very easy, right? Very easy to write a code because it's simple algorithm. Just that's the algorithm. Just very easy to write the algorithm, right? Right? So remember, still these are very small numbers. You are talking about numbers 128 digits and 128 digits. So, you know, to calculate it also manually, it's gonna take you forever. But to write a code for a C code or C++ code or Python code, it will take few lines to write it, right? All right. Another example in here. So 25 and 65. And by the way, it doesn't matter which one is bigger and smaller. You could start with the bigger or with the smaller, the same result. You could try it out. So the same thing, 25 and 60. So if you divide 25 by 60, how much is the quotient? 0. What is the remainder? 25. Move it 25 here, 16 here. Now 60 by 25, how much is the quotient? 2, because 2 times 25, how much? 50. And how much is the remainder? 10. 10 here. 10, 25. 25 divided by 10, how much? 2. How much is the remainder? 5. So what is the greatest common divisor in here? 5. Right? Switch it. Put 60 here and 25. The same thing will give you the same result. Doesn't make any difference. Okay? So it's a very nice technique to calculate the greatest common divisor, which we're going to use it later. Alright? It needs from you 5 lines of code to write like C code to the what. Right? So let's go to extended Euclidean algorithm. Okay? So given 2 integers A and B, we often need to find other 2 integers, S and T, such that S multiplied by A and T by B will give you the greatest common divisor for A and B. So the target here is A and B. I'm trying to calculate the greatest common divisor and using 2 arbitrary numbers. So the extended Euclidean algorithm can calculate the greatest common divisor for A and B, and at the same time calculate the values of S and T. So in the previous one, in the Euclidean, we were able to calculate only the greatest common divisor. Now we are able to create three things: the greatest common divisor plus a number s and a number t that achieve this relation. Why is that important? We'll take example. I'll tell you why is it important in a second. Okay. So that's what is the process in here. Okay, the same thing in here. So you have R1A, R2B, the same thing like Euclidean. Then you start with S1 equals 1 and S2 equals 0 and T1 equals 0 and 1. And you keep doing the process. So now you were able to calculate the greatest common divisor equals to 1. You are able to calculate S1, which is S, and T1, which is T. Okay, to achieve that. Okay. So here is the example. Okay. So given A 161, B 128, find the greatest common divisor and the values of S and T. So we need to get the greatest common divisor, which is 7, S is minus 1, and T equals 6. So what we do in here, 161, 28, so quotient, remainder, we keep going. And then how we calculate S1 and R1, so in here, if you look in here, you're going to apply this algorithm, R equals R1 minus Q times R2, right? So you go in here, so this is the Q, this is the R, S1, where is S1? Here, the S1 equals the previous S1 minus a Q, whatever the Q, multiplied by S2. And you keep going until you go to the end. So that's the Q, okay, that's the R, and you calculate it. You start with 1, 0 and 0, 1, and you keep going, right? Until you calculate the result. Okay, so let me write it for you. So you have R equals, you can see R equals R1 minus Q
into R2
times
R2
times R2. Okay. And then you have the S equals S1 minus Q times S2. And then you have the T equals T1 minus
Q times T2. T2.
2. So let's apply here, right? Okay. So what is S equals? S equals S1. How much is S1? 1. Minus Q times S2. How much is 2? 0. Times 5, 0. How much remain? 1. Let's do it here, for example. So it equals to S1. Where is S1? 0. 0 minus how much? Q is 2. How much is a Q? 1 times 1, 1. And there is minus, so 0 minus 1 gives you minus 1. Right? So on and so forth to the end. Okay? So until we come in here, so what is the value of S1? S minus 1. Same thing in here. You apply the rule and you're going to get with 6. T equals 6. Right? So that's extended Euclidean. What you get, the greatest common divisor, you get an integer T and you get an integer S. Alright? Fine. So for example, yes.
Sorry, is S1, S2, T1 and T2, are they default numbers? like constant?
Yes, we start, yes, constant, but we start with 1, 0 and 0, 1. And then you do the calculation according to the formula until we finish, okay? So, given A equals 17 and B equals 0, okay, what is the greatest common divisor and what is an T value? So, 17 and 0, 1, 0, 1, 0, so it's ended as a start, right? So what is the greatest common divisor for 17 and 0? 17, right? 17, right? So 1, 0, we don't go further. So once we see 0, we don't go further. So it's easy. In here, if you have A equals 0 and B equals 45, find the greatest common divisor and S and T. The same thing, 0 and 45. 0, 0, then the 0 move to 45. Then what is the numbers 0 and 1? Okay? Alright. So a linear Diophantine equation, it will be useful in many applications. Okay, so for example, A times X plus B times Y equals C. Alright, so let me ask you a question. Okay, if I tell you, give me the options for C equals $100, but how can you build $100 out of 5s and 20s only? Right? So for example, okay, I need $100 built of 5s, okay, and 20s only. So let's say for example, X or A is the 5s and B is the 20s. So you could, for example, have you could have 0 times A, which is 5, plus 5 times B will give you $100. You agree?
Yes.
Right? B how much? $20. 5 times 20 will give you 100. So what is the set in here? 0 and 5. Right? There's one option. Is there another option? So, for example, let's try this. 4 times B. Okay, how many has to be in here? 4 times A. Right? 4 times 5, 20. 4 times 20 will give you 80, total 100. So what's the other option in here? 4 and 4. Alright? So you need to know all the options that give you $100 out of 2 bills. Alright? That will be the one of the, so for example, we'll come to this. So in the linear Diophantine equation, there is a particular solution, x0 equals c over d times s, and y0 equals c over d times t. Okay, so that's why we need to calculate the s and the t. We'll be able to know particular solution. Or the general solution, it will be x0, which we calculated in here, plus k b over d, okay, and y equals y0 minus k over a over d. Remember, so where k is an integer. So, example, find the particular and general solution to the equation, this equation. Okay, so you apply the rules, you get x0 and y0. These are the rules, right? In here. Right? So what's x0 equals? C over d times s. Okay? Which gives you 5, and y0 equals 5 times minus 1 minus 5. And then you apply the general solution, which is x, whatever k is any integer. Give you multiple solutions. So, for example, imagine we want to cash $100 check and get some 20s and 5 bills. we have many choices which we can find by solving the corresponding Diophantine equation. 20x plus 5y equals 100. Since D is the greatest common divisor, which is 20 for 20 and 5, what is the greatest common divisor? Is 5. Okay? And 5 divides the 100. The equation has an infinite number of solutions. These are the solutions. 1, 2, 3, 4, 5, 6. 6 solutions. Infinite number of solutions. But only a few of them are acceptable in this case. The general solution with x and y notation give you this solution. So you could use this equation once you know the greatest common divisor, you know the S and T, to calculate the solution by applying these rules in here, the particular solution and the general solution. Is it useful? Sure, it's useful. All right. So let's move on to modular arithmetic. Okay, you know what's modular arithmetic, right? Well, so in modular arithmetic, the division is not important. What is important is the mod, the remainder. Okay, the mod, the remainder. So what is important? So when you say, for example, okay, 9 mod 4 equals how much? 1, right? 1, which is the remainder, right? Because 8 times 4 gives you 2, and the remainder is 1. So 11 mod 3 equals how much? 2, right? Okay, and so on and so forth, right? So in arithmetic, we don't care about the division, we care about the modular operation, the remainder, okay? So the division relationship is such that okay, so let's go there. So in a modular operator, the modular operator is shown as mod. The second input in is called the modulus, and the output R is called the residue, modulus and residue. So in the division, you know, we equating, and the remainder, we don't care about the equating, we care about the mod, the remainder, and it has to be non-negative. That means 0 or positive. 0 or positive. Agree? Alright? So let's take examples. So find the result of the following operation. 27 mod 5, what it gives you?
2.
2. Okay, 36 mod 12. 0 will give you 0 because 36 has 3 12s. 0. So minus 18 mod 14 will give you minus 4, right? But we have to convert it to what? To positive. So we add the value of the modulus. How much is the modulus? 14. So when you add 14 to minus 4, will make it 10. Alright? We'll make it 10. So always, if it's negative, you add the modulus to it. So again in here, minus 7 mod 10 will give you minus 7. Right? Will give you minus 7. So you add the modulus. How much is the modulus to it? 10. How much will give you the final? R. So you never give anyone a negative answer for mod. If it's a negative, you have to convert it back to non-positive, non-negative, 0 or positive. Clear? R. So set of residues. So the modular operation creates a set which in modular arithmetic is referred to as the set of least residues modulo n or Zn. So for example, so Zn, okay, if the modulus is n, so the set of the results will be from 0 to z minus to n minus 1. So if the modulus is 11, so what are the results? Could be 0 to 10. If the modulus is 6, what are the results? 0 to 5, right? So that's what we call it, set of residues. All right? Very simple. So z of 2 equals 0, 1. Z of 6, 0 to 5, and so on and so forth. Clear? So we have learned what we have learned, so modulus. Okay, we have learned about the mod operation, the modulus, and the residue. And then now we are learning about, and we learned that the result always has to be non-negative, 0 or positive, and we're learning about the set of residues. Nothing new, right? Like congruence is the way to write the operation. So to show that two integers are congruent, two integers are congruent, we use the congruent operator, the 3 dashes, for example. Okay, so 12 mod 10, so we say in here 2 and 12 are congruent to modulus 10. To modulus 10. That means that if you do the modulo for 12 will give you?
2.
Will give you? 2. And if you do the modulus, the mod operation for 2 will give you? 2. So if you do, okay, so if you say 12 mod 10 equals 2. And 2 mod 10 equals 2. So what we learn from that 2 and 12 are what?
Mod
Congruent. Are congruent when it comes to what? When it comes to mod
10.
So what are the two digits are congruent there? 2 and 12. But there's a condition, congruent when?
When the mod 10.
When the reference to mod 10. Look at the second one. Okay, 13 and 23, they are congruent to modulus what? 10, right? 23 mod 10 gives you how much? 3. 10 modulus 10 gives you how much? 3. Right? Right? You could add them, so you could say in this one, you could 13 is congruent to 23, it's congruent to 3 when it comes to what?
Mod 10.
To mod 10. Clear? Same thing with the next examples. Just take a look at them, right? Alright, so concept of congruence that, for example, you have a z which is the set of digits, okay, or integers, and mod, you take any one, mod 10, if you shift 10, all of them will be congruent. So minus 8, 2, 12, 22, all of them are congruent. So you could shift the modulus, it will be congruent. So z of 10 will give you from 0 to 9, and look in here, 22, 12, 2, minus 8, whatever, they are all congruent. So now we learned about congruence. We have two characters, and congruence has to be in reference to one. Okay, so a residue class A of an is the set of integers congruent modulo n. So these, for example, 0, these are congruent. So in here, for example, you shift like minus 12, minus 10. So what is the result here? 0. In here, 14 minus 9. So 14, what is the difference between 14 and 9? 10. 9 and 4, 10, and so on and so forth, right? So always the result is 1. So for example, 16 congruence 5, how much? 1, right?
Yes, 1.
11, 1, 6, 1, 15, 0, okay? This is, okay, this is from Okay, for modulo 5, what are the results for modulus? So when you say mod 5, what are the results? Are set from 0, 1,
4.
2, 3 to 4, right? You could apply this to z, right? To z, any integer, right? So the results, either 0. To get 0, these are the numbers that you could use. To get 1, these are the numbers you could use. To get 2, these are numbers you could use, right? And so on and so forth. What we call this congruent modulo n. Okay, set of integers congruent modulo n. All right? Clear? All right. So, comparison of z and zn. You know what's z? Z, the set of all the integers, positive, negative, including 0, right? Zn is the modulus for a number. Okay, so this is z. All right. So, for example, in here for 2, a is congruent to digit 2 mod n. So it will range from 0, 1, n, okay, from 0, 1, 2, 0, 1, 2, and then repeat itself, and then from here n minus 1, n minus 2. It's like it keeps circulating, okay? We use modular arithmetic in our daily life. For example, do you use modular? Use it in the clock, near a clock, right? It's modular 12, right? Right? So usually you don't say the time now is like 18. What do you say?
6.
6, right? Modular 12, right? So we use modular arithmetic in our daily life. For example, we use a clock to measure time. Our clock system uses modular 12 arithmetic. However, instead of a 0, we use the number 12. 0, we use the number 12, right? All right. So operations in Zn, the 3 binary operations that we discussed for the set Z can also be defined for the set Zn. What is Zn? Set of
Infinity numbers,
set of
positive and negative.
modulus. Okay, the results could be so, right? So when you say mod 5, what is the set? 0 to 4, right? All right. So we could do operations in Z or Zn. Okay. So for example, in here, a plus b mod n equals to what? To a mod n plus b mod n will give you c. Okay. So the point in here that when you do operation in Z or Zn, it will give you a set, again the set on the Zn. Okay, so we're doing operations now not on Z, on the modulus. Let's take examples. So for example, perform the following operations. The inputs come from Zn. So add 7 to 14 in Z12. Okay, here. For example, 14 plus 7, mod 15. Okay, mod 15. So what you could do, you could say 14 plus 7, how much? 21. Mod 15 give you 6. Or what you could do, 14 mod 15 plus 7 mod 15. Let's try it. 14 mod 15, how much it give you? 0. Okay, 7 mod 15.
7. 0.
Huh?
0.
It give you 7 mod 15. 0 gives you 0. How much? 1 maybe, right? 1, right? And 14 mod 15. 1, right? So 1, so it's 1 plus 1, right? How much?
2.
2. 2 mod 15. Is this 1?
So
Okay. We'll come to it. So now you know what we are doing. So 7 minus 11 minus 4. Mod 13 minus 4 plus 13. 9. No? Right? 9? Right? 9, right? I think so. So 7 minus 11 is minus 4. So minus 4 mod 13 will give you minus 4. So you need to, minus 4 plus 13, how much? 9. Give you 9. Clear? Let's take the multiplication. 7 times 11, 77. Mod 20 will give you 17. Right? Right? So, anyways, so perform the following operations. The inputs come from the z, whatever, z or z and n. So, same, we did this already. So, what are the properties? Let's take a look at our first property. If a plus b mod n, okay, it will equals a mod n plus b mod n, everything mod n. So 3 times, right? So in here, a minus b, it will be a mod n minus b mod n, everything mod n, 3 times. Same thing in here, right? Alright. So let's take a look. And that's why we need these techniques, not for the small numbers. So for example, in here, I mean, if you have this huge number plus this huge number mod 11. So what you have to do, okay, you calculate the mod 11 for this will give you 8. And you calculate the mod 11 for this will give you 9. Alright? And then everything mod 11. So 8 plus 9, how much? 17. Mod 11 will give you 6. Same thing in here and here, okay? Same thing in here and here. And that also very easy to write a code for it. Also, when it comes to for powers of 10 when divided by integers. So for example, 10 to the power n mod x will equals 10 mod x. So remove the n and everything then power it to n. Okay, applied third property n times. Right? So what you do, for example, 10 mod 3 is 1. Alright? So 10 to the power n mod 3 equals 10 mod 3 and everything to the power n gives you 1. Right? Look in here, 10 mod 9 gives you 1. So 10 to power n mod 9, you calculate 10 mod 9 and then to power n. Same thing applies here, right? Just remove the n, the power, and then everything, the result power the result. This is the property, okay? So we have been told in arithmetic that the remainder of an integer divided by 3 is the same as the remainder of the sum of its decimal digits. So we write an integer as the sum of digits multiplied by the power of 10. This is an easy thing that you know. So for example, 6371, how you can write it? You can write it 6 times 1000, 3 times 200, 100, 7 times 10, tens, right? And 1 times 1, right? You could write this number, this. So when somebody tells you calculate the mod for this number, you could spread it like this out, okay? And now what we said, if we need to calculate, for example, you know, the mod for 10 to the power 3. It equals to the mod of 10, and everything will be powered to 3 at the end. So that's what we did in here. So for example, an 10, okay, anyways, that's the rule in here. And by the end, you calculate to the mod of 3. Now, very important topic is inverses. You know, there is addition inverse. How much time we have? Okay. So we have, inverses. So for example, in Gn, two numbers A and B are additive inverses. When they are additive inverses, if you add them together, will give you 0. Right? So what is the additive inverse to 5? Minus 5. Right? So A plus B will mod n will give you 0. All right. So if you do the mod, will give you 0. So modular arithmetic, each integer has an additive inverse. Each integer has additive inverse. The sum of an integer and its additive inverse is congruent to 0 modulo n. All right. So let's take an example. Find all additive inverse pairs in Z10. So Z10 includes, what are the digits included in Z10? 0 to 9. So we need two additive inverses. And remember, we're working in modulo what? 10. Okay. So let's take 3 and 7. 3, 7, are they what do you call it? Modulo inverses?
No.
Yes. Why? Because 3 plus 7, 3 plus 7, 10.
Yes.
Modulo 10, 0. Okay, 2 and 8.
Yes. 10.
Okay, so all of them adds to 10 or 0. Alright? So basically every integer has additive inverse. Remember, we were talking about additive inverse for modulo. Right? Alright? Easy. That's very easy to calculate, right? Now let's talk about multiplicative inverse. That if you multiply the two digits, will give you 1 modulo n. 1. Okay? So in modular arithmetic, an integer may or may not have a multiplicative inverse. When it does, the product of the integer and its multiplicative inverse is congruent to 1 modulo n. Okay? So let's take example. So find the multiplicative inverse of 8 in Z10. So what is the number? You multiply it with 8, you do the modulo, will give you 1. So there is no multiplicative inverse because the greatest common divisor between 10 and 8 equals 2, not equal to 1. So the condition to have multiplicative inverse, that the greatest common divisor has to be 1. Okay. So let's take a look. Let's take at the multiplicative inverses in Z10 in general. So 1 is a multiplicative inverse of 1. Why? 1 times 1 equals 1. Modulo 10, how much will give you? 1. Okay. 3 times 7 is 21. Modulo 10, how much will give you? 1. So they are multiplicative inverses. Okay, 9 times 9? 81. Modulo 10? Give you 1. So what are the numbers that have multiplicative inverses in Z10? 0, 3, 7, and 9. That's it. The rest of them don't have multiplicative inverse. So numbers 0, 2, 4, 5, 6, and 8 do not have a multiplicative inverse. So the rule is what we are learning here. We need to know how to calculate multiplicative inverse and addition inverse or additive inverse. Every number will have additive inverse, but not every number has multiplicative inverse. Alright, very important. So find all the multiplicative inverses in Z11. So let's try it. So Z11, okay, 1 and 1. 1 times 1, 1. Modulo 11 will give you 1. That's easy, right? Let's try this 3 times 4. 3 times 4, 12. Modulo 11 will give you 1. How about 9 times 9? 81. Modulo 11,
7.
4.
4.
4.
is it 4?
7. 4.
11 times 7, how much? 77. So,
So 9 times 9 is 81.
Yeah, it's 4.
So it's gonna be 4.
4, then it's not then why they put it there? It's not multiplicative. The result has to be how much? 1, but it's not. Then it's not multiplicative. There's some mistake in here. Okay. 10 times 10.
1.
100, right? So 99. There is 1. That's correct. Okay. All right. So the extended Euclidean algorithm finds the multiplicative inverse of P and Zn when n and b are given. N and b are given, and the greatest common divisor has to, for n and b equals 1. The multiplicative inverse of P is the value of t after being mapped to Zn. So again, so if I need to calculate the multiplicative inverse, the same thing. So for example, I have 26 and 11, right? All right. So if I need to have the multiplicative inverse of 11, Z26, 11, okay, here, the Z26. So I put 26 in here and the 11 in here. So you know how we did that, right? Quotient and remainder, and then until we go to 0 in here. What is this one in here? Is the greatest common divisor. So does it apply? Yes, because the condition, the greatest common divisor has to be 1. So 1, right? And then I calculate the t as we learned before. So when I calculate the t, when I come to 0 in here, and this has to be 1, okay, then I can get the multiplicative inverse, which is -7, okay, all right, and or I mean, you add the 26 to it, it becomes 19. Okay, so I could use Euclidean to calculate the multiplicative inverse for any number. Right? When you have a huge numbers, it's very hard to calculate it by hand, right? So you have to have an algorithm. This is the algorithm you could write to do that calculation. Agree? Wow. Another example, find the multiplicative inverse for 23. So 23 for Z 123. You go all the way until 0. This is 1, then it's good. All right? And I calculate the t. Okay, so what is multiplicative inverse? -13. Okay, I add it to 100. I add 100 to it to convert it to positive. It becomes how much? 87. Okay, 87. All right. Here, for example, for 12 and 26, same thing. Can I do it?
No,
No, the inverse does not exist because.
it's 2.
Yeah. Okay. If this is 1, then I take this. Okay. So as you see in here, addition and multiplicative table. So, I mean, this is the addition table. The multiplicative, not everyone. This is for Z10, right? All right. So different sets. So Z7, whatever. So when we need to use Zn, when additive inverse are added, we need to use Zn asterisk when multiplicative inverse are needed. So this, with the asterisk, means we are looking for multiplicative inverse set. Okay, multiplicative inverse set. So Z6, this is, it will be, because we said in additive, every digit has inverse, right? So the whole set. But in here, what does it mean? not, this is only the numbers inside the Z6 that have multiplicative inverse. Okay? Two more sets, cryptography often use two more sets, ZP and ZP. What's ZP? Set of prime numbers, right? The modulus in these two sets are prime numbers. So Z13, it's from 0 to 12, and Z13, the multiplicative inverse to 12. Why? Why it has multiplicative inverse for all the digits? Why? Because it's a prime number. So when you have a prime number, all the digits they have multiplicative inverse. Good? Matrices quickly, I might leave it for you to go over it, but you know, I mean, we have done matrices, we have n columns, so we have to know row matrix, column matrix, square matrix. This is 0 matrix, 1 identity matrix, we call it identity matrix, right? So you know how to add matrices together, right? Each element, so 5 plus 7, 12, 4 plus 2, whatever, 2 plus 2, 4, 4 plus 1, 1 plus 3 gives you 4, and you know how to subtract. Then for multiplication, that the number, you know, there is a condition that you know shows the product of a row matrix 1 times 3 by a column matrix 3. The result is a matrix of 1 by 1. So it's, you know, 1 by 1. So 3 by 1, and all of that. So you know, this is for multiplication. The rows, and you know how to multiply this one. Okay? This is like multiply a digit by scalar multiplication, we call it. So you multiply 3 by each number, and that will be the value. So 3 times 5, 15, 3 times 2, 6, 3 times 1 equals 3, and so on and so forth, right? You need to determine, you have to know how to calculate the determinant of a square matrix. Determinant is only calculated for a square matrix, okay? So take a look at that. And that's how you calculate the determinant. Multiply this by this minus this times this. So A11 multiplied by 2, A22 minus, okay? Determinant, and how is it for multiplicative inverse are only defined for square matrices. Alright, so you have, this is A and this is A inverse. What does it mean? If you multiply A with A inverse, will give you what? The identity matrix. The identity matrix. Nothing is special in here. Nothing is special. I mean, you could take a look at it. I mean, just a few more slides because the time is up. Thank you so much. I'll post the assignment for you. Please do the assignment and do the lab. Thank you.